Recording in progress.
Look at me like I'm crazy when I shut my feelings down. You look at me like I'm different. Still you stay cause you feel something real. Get so lost in my moments. Doesn't mean I don't need you. I fell in love with your colors. They kinda tell me what I'm thinking. I fell in love with the way we are and the way we lose it. There's something different about us and the reason why we stay. We fly around like paper planes. They never know where we will fall. Nobody can see us. Still they wanna tear us apart. There's something different about the way we are.
How are you doing today?
Pretty good.
Oh, you can hear me. That's excellent. Everything seems to work today. I've been having problems with my microphone over the past couple of weeks, and it's all worked great this week, which makes me nervous because last week it was not working. I was having these problems, not on this stream, but on the other one, where I would have to reset all my audio gear at the beginning of the stream. It would take me about 5 minutes to do that. So it was really making me nervous about that, but it seems to be working this week.
What kind of microphone are you using?
Oh, this is just a lapel microphone, a wireless one. So it's not actually a problem with the microphone, it's a problem with the mixer. The mixer was not communicating with the computer. I think what the problem is the USB cable might have been a little loose, and so the mixer would lose communication with the computer and wasn't able to send the audio back to the computer. So wouldn't hear anything. But there was apparently nothing was obviously wrong because I could see the audio meters going up and down and just couldn't hear anything. And so I would have to power cycle the mixer and then unplug and plug in the USB cable, and then it would work for a day. And then it would just stop working. So what I actually suspect is maybe the kind of no-name brand USB hub that I got that it's plugged into might be it wasn't expensive, so it might be failing. And it's not that old either. You people are saying I'm low frames per second.
It's just a little laggy.
Let me see if I can fix that. Let's try this.
Probably just because it's so high quality.
How about that? Is that better? Oh, I've heard of this before. This has happened before. The normal little thumbnail is okay because that's a fairly low bitrate video. It's the big one that is, much higher quality and requires more bandwidth. And so, what did people do to...
Yeah, what's the bandwidth of your uplink?
Oh, 20 megabits.
Yeah, that's what I got too.
I remember last year, somebody said there was something they could do in their Zoom and it would kind of fix it. It was on their end they could do that.
It actually looks good now.
No
lag anymore.
So what I can do on my end is there's actually 2 bit rates that Zoom can send it out at. There's the normal one, which is fine for doing what I'm doing here. It's just a talking head, or you're putting presentation slides on the screen. So not much is changing on the screen, and so it can use a fairly low bandwidth uplink to Zoom. But if you want to do something like play a video, then you can tell Zoom, I'm sending a video, increase the bandwidth, and then it will send more bits down the pipe. And so that's what I just did, is I just selected that option to say, please increase the bandwidth. And so that could help with the problem. But, and then it goes through Zoom servers, and then Zoom does all of their stuff to uncompress the video, multiplex it in with all the webcams, and then recompress it and send it to you. So there's like a lot of different links along the path where there could be problems. Some of them are in my control, some of them are not in my control. But I hope at least it's decent enough for you. And like I said, for the most part today, we're just going to be looking at slides, so you don't need a whole high amount of bandwidth.
Do you know if the stream actually goes through Zoom servers? Because I was under the impression that Zoom uses WebRTC, which is a peer-to-peer sort of connection.
Maybe if you're only doing like a one-to-one Zoom, but since we're doing a one-to-many, it's got to go through their servers in order to get all the videos sent to the right people.
Okay.
And also there's a little option you can click on. It says like information about this meeting, and it says you are connected to the Zoom global network via data centers in the United States. So it does go through their stuff. Of course, I'm also simultaneously streaming to YouTube. That's using about 4 megabits. So I got 4 going to YouTube, and I got about 4 to 6 going to Zoom. So I got about 10 going all together. So even though I got a 20 uplink, you really don't want to use more than about half of that. So I'm kind of bumping up against that limit. But I did have to get Xfinity's upgraded gigabit service, and I say quote-unquote gigabit because it's not really, just to be able to get the higher uplink speed. Most people don't.
You get the gigabit download, but you don't get the upload.
Yeah. It's still asymmetric, right? But it's like, okay, you got the faster download, we'll give you a slightly faster upload. I wish I had the one that was totally symmetric. Because honestly, most people don't need gigabit download. If you're just watching Netflix or YouTube, that's only using about 4 megabits in bursts. So, despite the marketing, even a family of 4 to 5 people don't need maybe more than about 100 megabits. Really? So the gigabit gives you faster downloads when you have something large to download, like you're downloading updates to your phone or your operating system. But other than that, you don't really need it. And of course, Xfinity is really generous. They give you that gigabit speed, but they don't up your cap. So they tell you, if you have more devices on your network, you're going to need faster rates. Like, well, yeah, but you're also going to need like more data in general, and they don't give you any more, right?
What's your cap at?
It's their standard, like 1.2. Although, because I have teenagers in the house, I had to get the unlimited. So I'm spending an extra $50 a month just because the teenagers just leave their TVs on all day, even when they're not here. Like, I have to go to their rooms and turn off their TVs. Like, you're not here. Stop streaming this stuff. and even make it as worse. When they are here, they're watching their TV, and they have something else playing on their laptop, and they have something else playing on their phone. So, like, they can watch 3 things simultaneously somehow. I don't get it. Like, pick one, please. Just watch one. Yeah, so I'm also restricted by other, like I said, there's all sorts of, it's not an easy system where you're just sending video from one to another. It's sending video to Zoom, and then Zoom is doing their stuff. And then it goes, of course, there's Xfinity on my end, and there might be Xfinity or AT&T or SureWest on your end, and then there's a bunch of moving parts that, like I said, not all of which I have control over. So it's a complex answer.
Yeah, I'm not I don't know too much about WebRTC, but I know that Discord uses it for their communications, and it's how they were able to kind of survive as a startup because they didn't have to pay as much for server costs since they were able to use the peer-to-peer connections.
Well, let's kind of get started on the stuff we're going to do today. Sorry, I just accidentally launched Final Cut Pro on my computer just by accidentally clicking on the button, and so I had to wait for it to go through all of its startup stuff just to quit it. Oh, song kind of slaps, huh? You know what happened was I used to just stream like Pandora or Spotify on my stream, but then when I started doing this simultaneously to YouTube, YouTube has that aggressive content ID filtering system where they would detect if something was a copyrighted song and they would just mute your stream. And then we'd like flag you. You get a little nastygram from them that says, "Hey, you're playing music that's copyrighted." So I had to switch over to a service where they would handle all that stuff for me. So it means I can't play the stuff I used to play. I now have to play their stuff. But you like this, huh? All right, we're done with music. Let me just pause it. There we go. Okay. So last time we talked about signed integers. We did 2's complement, sign magnitude, and excess n. And there were those 3 representations. So today we're going to talk about how do you represent non-integral numbers, numbers that aren't integers. So I'll start with this question. I'm going to give you this bit sequence, 110.101. I'm going to ask you, what do you think that is? What value do you think that is? Just like put on your thinking caps and try to figure out what that is. I haven't told you, but like put it in the chat or something and what you think the value of this number is. Any guess? Oh, good question. What's the context? So it is it's obviously a fractional number. It's in binary. So try to figure out what its equivalent base 10 value would be. How about this? I'll give you a hint. The left side of this is 6. What's the right side? 6 point something. So we got a couple different answers here. I've got 6.5. 6.625. Well, 6.625 is the answer I'm looking for. And the reason why that is because if you just continue these powers of 2 past that radix point, that's what this thing is called, is, point to it over here, this is the radix point. If you're working in base 10, it's called the decimal point, but if you're working in any other base, it's called the radix point. So once you go past the radix point, you just continue these powers of 2, except you go into fractional powers of 2. So the first place after the radix point would be your halves, and the next one would be your quarters, and then your eighths. So this number here is 2 squared. This is 2 to the first power, 2 to the 0 power, 2 to the negative 1, 2 to the negative 2, and then 2 to the negative 3. And then you just add up those values. You've got 4 plus 2 plus a half plus an eighth. And that gets you 6 and 5/8, or 6.625. Okay? So these are called fractional numbers because they don't represent whole numbers. They're not floating point numbers yet because the decimal place has to be in one spot. And also because we're using an actual decimal spot or a radix point to represent where that is in the number. Later on today, what we're going to find out is how can you represent a fractional number, one with a radix point, but all you have are ones and zeros. So you need some way to represent where that radix point is using just ones and zeros, and that's where we're going to get to. But these here are called dyadic fractions. It's a fancy term. It basically means a fraction whose numerator is odd and whose denominator is a power of 2. An example of that would be 3/8 or 11/16 or 17/32. And so we actually use dyadic fractions all the time, at least here in the United States. We use them on things like rulers. When you measure your inches, we measure them in fractions, and the fractions always have a power of 2 on the bottom, and they always have an odd numerator. You just never knew that's what the name of it was. So now that you know how to represent a fractional number using ones and zeros and a radix point, try converting these. Let's do 13.75. That's a base 10 number. Try converting that into binary. You can just use the spending method. $27.375 and 7.6.
Rồi tiền để cả đám cho hả?
Không đang thu hết mà. Oh.
So try doing those numbers, those three numbers. You can just use the spending method. So start writing out your powers of 2. Start with your whole powers of 2, go to that radix point, and then go into the fractional powers of 2. And then just spend all the money. So see what you come up with. Give that a shot. Now, while you're working on that, if you're kind of stuck, you have no idea what to do, I'll kind of like start writing it out on the screen so you can see it, but I'm not going to say anything until we're done with this. Okay, so the answer to the first one is 1101.11. And if we just write out the powers of 2, we've got 8, 4, 2, 1, and then our radix point, and then a half, a quarter, an eighth, 16th. You just go as far as you need to. And then we just start spending. I can buy something for $8, I can buy something for 4 and then for 1, and that spends the $13 of my $13.75. And then I can spend a $0.50 and then a $0.25. That's 75 cents, and that uses up all my money. So here is this fractional binary representation of 13.75. So now that you know that technique, go ahead and try it on the other two. Okay, let's see what we got there. Some people have already put in the chat their answers, and those look good. So we're just going to spend away. We've got $27.37.5 to spend. So we'll buy something for 16, and then for 8, that's $24. So we got 3 left plus the change. Nothing for 4, and then 2 and 1, and that's our $27 right there. So we have 0.375 yet to spend. So it looks like we can't buy anything for a half. That's 0.5, which is more than we have. But we can buy something for a quarter, which is 0.25. So we'll spend that, and that leaves 0.125 left over, and that's what an eighth is. So we'll spend that, and now all of our money is gone. Okay, last one. 7.6. We're going to do 8, 4, 2, 1, point, a half, a quarter, an eighth, a 16th, 32nd, and then we'll start spending. So 7 is 111 point, and then we have 0.6. So I can spend 50 cents. There's that. And that leaves a tenth of a cent, not a tenth of a cent, a tenth of a dollar left over, 0.1 left over. So nothing for a quarter and nothing even for an eighth. But we can spend that 16th, and that leaves a little bit left over. So we can spend the 32nd, and that still leaves a little bit left over. So we're going to need some more. And it turns out we have more than, less than a 64th. So we can't spend that. It turns out that this just goes on forever. $7.6 cannot be represented exactly in binary. Seems kind of strange, right? You got this nice roundish figure, in base 10, but it can't be represented in binary. It just, you'll never be able to spend all the money. There will always be a little bit left over. This may seem a little unusual, but really, you've seen examples of this. You know that numbers like a third, which is a nice round fraction, can't be represented exactly in base 10. The 0.3s just go on forever. You know, there are some other fractions that are like that. I think like 1/11th, you know, is also like that. It just keeps going on forever. You can't ever write down enough digits. So you just have to stop somewhere and say, that's good enough. Now, one question you might have right now is, why is it that a number can't be represented exactly in binary? And the answer has to do with the factors of the number. You see, a tenth, you know, or 10, if you will, has factors of 2 and 5. And it's that factor of 5 that causes the problem. The factor of 2 makes it easy. Right? Anything that has a factor of 2, and only a factor of 2, can be represented in binary very easily. But that 5, since 5 is not a multiple of 2, there's no way to write down multiples of 2 and have them add up to 5. So that's where the problem is. So one way to send or transmit or represent fractional numbers is to use a fixed point representation. For example, I could say, or let's say you and I want to send some numbers back and forth to each other. We have to agree ahead of time on how we're going to use those ones and zeros. The first thing we'll have to agree on is how many bits are we going to use. Let's say we're just going to use 8 bits. Keep the numbers fairly small. We're going to use 8 bits, and we're also going to agree ahead of time that the radix point is going to be right in the middle. 4 bits on the integer side and 4 bits on the fractional side. Now, we could agree on a different standard. We could say maybe there's going to be 6 bits on the integer side and 2 on the fractional side, or we could do like 5 and 3, or we could do 1 and 7. Right? As long as we agree ahead of time on where that radix point is, then we can just write down our ones and zeros and encode and decode them as appropriate. So this number here, now if we were actually sending it, we would actually send 1 1 1 0 1 1 1 0 0. This is what we would send to recipient. And the recipient would receive those 8 bits, look at our standard representation, and know that there is a radix point that goes right in the middle. And that tells them where to split up the number between the integer and the fractional side. So because of that, we know that this is, this portion here is, what is that, 13? And this portion here is 0.75, and so this is 13.75. So here's my question to you. I got 4 questions for you. What is the smallest or minimum value that this representation can hold? What's the smallest number? And then what's the biggest number? What's the maximum number that this representation can do? We'll start with those 2 questions. What is the smallest number that this can do? What do you think it is? Right, it's 0. People in chat are posting 0. It's 0 because the smallest value you can do is 0.0000. And this would just be 0. The largest value would be all ones. That's the largest integer portion we can do, and then the largest fractional portion. So what is that value? The number to the left of the radix point is 15. And the number to the right of the radix point is 15 sixteenths, or 15 point, people are posting in the chat, 15.9375, 9375. That's the largest number we can do with this particular fixed point representation. So we can write out these numbers on a number line. Here's 0 all the way on the left-hand side. Here's 15.9375 on the right-hand side. And my next two questions to you are, what are the next values up from the minimum and down from the maximum? So here's 0, which is the minimum number we can represent. What's the next one? What's the one that's, one up from that? And here's the maximum number. What's the next one down from that? Good. So the first one up from the minimum is 1/16. That would be 0000.0001, which is 1/16. And the second greatest number, the one that's just one down from the largest number, is 1111.1110. And this would be 15 and 14 sixteenths, which is 15.875. And then bonus question for you. If I was to write out all the numbers on this number line from least to greatest, how many numbers would there be? How many tick marks would I put on this number line? $256. Very good. Why 256? Because we're using 8 bits for our representation. With only 8 bits, there's 2 to the 8th, or 256 possible numbers we can represent. So in between 0 and 15.9375, there are 254 other values in there. Okay, so now I've laid down the foundation of how to represent fractional numbers using just ones and zeros. You know this idea about doing the spending method, right? You call it the halves and the quarters and the eighths and the sixteenths. We're now going to apply that and see how we can represent floating point numbers. We just looked at fixed point, where we agreed that that radix point is going to be in a certain spot. But floating point means we can now move that around. We can have numbers that have a larger integer value and a smaller number of fractional values. Or we can flip it around, a smaller integer value and a larger, more precise fractional value. That's what's called floating point. So you can move that radix point around. So floating point numbers are essentially scientific notation, but in binary. Here's a base 10 scientific notation number. If I wanted to send this number to someone else, don't worry about binary for now. If I just wanted to send this number to someone else, and all I was using was just the numbers 0 through 9, there's some information in here that really is sort of redundant. It doesn't, I don't have to send it at all. In particular, I don't have to send this times 10. Everyone knows that's part of scientific notation. Every single scientific notation number has that there. So it's redundant information. I don't really actually need to send that. What I do need to send is the exponent. That's important. And then this piece out here in the front called the mantissa. The mantissa and the exponent are the two important parts of scientific notation. That times 10 part is really redundant, and I don't actually have to send that because the receiver knows that that's what they have to do when they receive the numbers. So if I wanted to send this number to someone else, I could get rid of that redundant information, and maybe I could just send negative 652127. And just like with fixed point representation, we would have to agree ahead of time on how to split that number apart and turn it into its pieces. And so we might agree that the exponent is always going to be 2 digits. And the mantissa is also always going to be the remaining numbers. And we might actually go a step further and say if we're only going to be sending digits, then we'll replace that minus sign with either a 1 or a 0. This would then become 1652127, where the 1 is the sign, the 6521 is the positive part of the mantissa, and the 27 is the exponent. So let's see if you can use that information to decode a couple of numbers. What is 0315206? And what is 1724, let's say 38? So what's this first number? We're decoding this. We're splitting it up into its sign, mantissa, and exponent parts. And then from there, we can assemble a scientific notation number and figure out what this is. Don't worry about like converting it out of scientific notation into the base 10 number. So this first number is positive 3.152 times 10 to the 6th. Right. The 06 here became the exponent. The 3152 became the mantissa. And the sign is positive. And then this second number down here is negative 7.240 times 10 to the 38th. Oh, and Andrew's got a great question. Something I just kind of glossed over here is how do you represent negative exponents using this? And you're right, that is a kind of a little shortcoming. Maybe we could use the that tens complement we were talking about last time to do something like that. Anyway, this is just really a hypothetical example for me to kind of lay down the pieces to do this actually in binary. Okay, so So what I wanted to show you with that example is we can take a scientific notation number, throw away the redundant parts, replace the positive or negative with another digit, and then just transmit just a sequence of digits to the recipient. And the recipient knows how to decode that number, break it up into its individual pieces, and then reconstruct the original scientific notation number from those pieces. That's what I want you to get out of that. So the last thing I want you to put into our kind of toolbox of techniques is that I can take a number like 0.0314 and I can convert that into scientific notation. And the way you do that is you just move the radix point either to the left or to the right until there is a single digit in front of it. And then you just adjust the exponent to take into account how far you move that radix point. So 0.0314 becomes 3.14 times 10 to the negative 2. So if I want to reconstruct the original number, I take the 3.14 and I move the radix point to the left by 2 spots. That's what the negative 2 means. And that allows me to reconstruct the number that I started with. So this representation on the left is called unnormalized. And on the right, it's called normalized. Because it has not only been converted into scientific notation, but it also follows the rule that there has to be just one single digit to the left of the radix point. Let's do another one. 65.21 and 1, 2, 3, 4, 5 times 10 to the 7th. So we want to take those unnormalized numbers and normalize them, turn them into scientific notation with the added characteristic that there can be only one digit to the left of the radix point. (65.21) becomes 6.521. We just move this radix point one spot over to the left, and so the exponent becomes 10 to the 1. And then finally, the bottom example becomes 1.2345 times 10 to the 11th. So the exponent was already 7, but we moved the radix point over by 4, and so we had to adjust the exponent to become 11. So this is normalized scientific notation. There's always just one single digit in front of the radix point. Great. So I've laid down all these pieces that we need to be able to do floating point notation in binary. Let's do that next. Okay, 6.375. I want to write that out in scientific notation, but in base 2. So the first thing to do is convert this into that fractional binary notation that I've showed you already with the radix point there. Just go ahead and just do a straight binary conversion. So write out the powers of 2, 8, 4, 2, 1, point, 1/2, 1/4, 1/8, as many fractions as you need, and then start spending. 6 is 4 and 2, so there's no 8s and there's no 1s. And then 375 is no halves, but it's a 1/4 and an 1/8. Okay, so all we did was just took our base 10 number and just converted it into base 2. It's not in scientific notation yet. It's still unnormalized, So the next step is to normalize it, convert it into scientific notation, but in base 2. That means we're going to take this radix point and we're going to move it to the left so that there's just a single digit in front of the radix point. Now we're not going to move it all the way to the left so that there's a 0 in front. We want to move it so that there's a 1 in front. So this becomes 1.10011. So I just took this radix point and I moved it over. And there's still going to be an exponent. So it's times 2, because we're doing it binary, not 10, 2. And then I'll just write out the exponent in base 10 just to preserve my sanity. So I moved over the radix point by 2 places. So I'm just going to put 2 up here. Okay, if I was doing this strictly in binary, I would say 2 to the 10th, right? But it starts looking weird after a while. So I'm just going to do the exponent in base 10. Okay, so here's 3 of them for you to do. 13.125, 1.9, and 0.0625. Try to write them in normalized scientific notation in binary. So use this technique I just showed you here. Start out with the spending technique and then normalize it. Go ahead and write your exponent in base 10. It'll be fine. So I'll give you a couple of minutes to work on that, and then we'll see how you did. Realized I didn't have my video on for you Zoom people. You weren't seeing me up in the corner. So now you can see me. Oh, you like the game show music? I should find the Jeopardy theme, right? No pressure, right? I'll just play the Jeopardy theme. Or if you're watching from Britain, I'll play the countdown theme. But that'll only give you 30 seconds to do the problem. Okay, let's see how you did. So first step is to convert 13.125 just straight into binary. So using the spending method, I've got 8 plus 4 plus 1. And then to the right of the radix point, I have 0.125. That's equal to an eighth. So I've got 0 for a half, 0 for a quarter, and then 1 for an eighth. And then to normalize them, I need to move that radix point. So it's sitting here after the 1101. I need to move it to the left by 3 spots. And I end up with 1.101001 times 2 to the third. Now for 1.9, I have a 1 dot and then 0.9. So I've got a half, and that leaves 0.4 left over. So I can take off a quarter, and that leaves 0.15 left over. So I can take off an eighth. That still leaves a little bit left over. So if you work this out, you've got an additional 001 on the end, and you've still got something left over. And so at some point, you just need to stop. You can say that's good enough. We'll figure out where's an appropriate place to stop in a little bit, but at some point you just have to stop. And now we can convert this into scientific. Actually, it's already pretty close. 1.11001 times 2 to the 0, because we didn't have to move the radix point at all. And then the last one is 0 point, and then 625.0625. I think that's like a 30, is that a 16th? I guess it's a 16th. So we got 0001. To normalize that, we're going to move the radix point. How many places is that? 4 places? 1, 2, 3, 4. Yeah, 4 places. So we got 1.0 times 2 to the negative 4. Okay, so now we have all the pieces we need to be able to represent a number in floating point binary representation. We have to take the converting it into a fractional binary number, which we just did, normalizing it into a scientific notation binary number. And then we're going to pull from the stuff we did on Monday. We're going to pull sign magnitude representation, and we're going to pull XSN representation. We're going to need all that stuff to represent floating point numbers in binary. So there is a standard called the IEEE-754 standard. IEEE is the International, actually I think it's, I don't remember what it stands for, but it's basically a consortium of engineers who meet to come up with standards like this. And this is document number 754, which says this is the way computers are going to represent the fractional decimal numbers in a floating point representation. And their standard sets down representations for 32 bits, 64 bits, 128 bits. I think they even go as high as 256 bits. And what they basically do is they take, let's say, the 32-bit quantity, and then they split it up into those 3 pieces that I talked about. Some of those bits represent the exponent. Some of those bits represent the mantissa, and one of those bits is needed for the sign out in front. So you've got the sign out in front, the mantissa portion, and the exponent portion. And the exponent portion uses a representation where they can do both positive and negative numbers. Now, for our purposes, 32 bits is just completely unwieldy, right? It's just too many to write down. And so what I'm going to do for our representation is just use 8. I'm just going to use 8 bits. I'm going to break it up in a similar way. Some of the bits will be exponent, some will be mantissa, and one of them will be for the sign. And I just want you to realize the real IEEE 754 just takes that and scales it up to 32, 64, 128 bits. We're just going to do it with 8. So we're using this modified IEEE 754. So the way I'm going to do it, and this was just sort of arbitrarily decided by myself, and again, if I want to transmit this information to someone else, then both parties would have to agree on how to break up these bits. But I'm going to say that the first bit is the sign bit. The middle 4 bits are the exponent. And the last 3 are the mantissa. And this is laid out the same way that IEEE 754 is laid out. The sign bit is the most significant bit, followed by the exponent bits, followed by the mantissa bits. It does seem like it's a little bit backwards. The scientific notation is sign, mantissa, and then exponent. And this representation has the exponent and the mantissa flipped around. There's actually a very good reason for that. But that's just the way this happens to work. So it's sign, exponent, and then mantissa. So I'm going to walk you through the process of taking a number like 13.75 and converting that into this floating point representation that's very similar to the real one used by your computers whenever you have to do fractional calculations. So the first step is to take care of the sign. That's easy. 0 is positive and 1 is negative. This is a positive number, so we're just going to put a 0 in the sign spot. Next step, convert this into a dyadic fraction. That's just the spending method. So 13.25, we got 8, 4, 2, 1, point, 1/2, 1/4, 1/8, and so forth. And so we've got 1101.01. Third step, normalize that into binary scientific notation. (1.10101) times 2 to the third. Because we just took this radix point and we moved it over by 3 spots. All right, so now we've got our mantissa and we have our exponent. Let's take care of the mantissa. Now our mantissa uses 1, 2, 3, 4, 5, 6 bits. But we have set aside only 3 bits for the mantissa, so we're going to have to get rid of some of them. Which ones should we get rid of? So we have 6, but we can only use 3. Well, we want to get rid of the bits in the mantissa that change its value by the least. So if we had to round, let's say you had a base 10 number, and you had to round it to like the nearest hundreds, you know, which ones should you round, right? You should round the ones that change the number by the least. And so that would be the least significant digit. So we're going to chop off digits from the right-hand side. But we have one little trick up our sleeve. We have one trick that we can do. I flip back to the previous slide. Look at these normalized numbers on the right-hand side. Every single one of them begins with 1 dot. 1 dot, 1 dot, 1 dot. Whenever you normalize a binary number, that number that's always to the left of the radix point is always going to be a 1. So that means that's redundant information. We don't have to put that on our representation because when we send that information to someone else, they'll know to just put that back. That essentially gives us one additional bit of precision in our mantissa. Since the mantissa is always going to begin with 1 dot, we can just drop that off. Okay, so 1.10101, we're going to keep the 3 bits right after the radix point and then drop off the 1 dot because it's redundant. It's extra information. And Andrew's got an excellent question here. This is one that I'm glossing over for now. How do you represent the number 0, which is going to be 0.000 times 2 to the 0th? In this modified representation, you're absolutely right. I can't represent 0. In the real one, there is a representation for 0. If we get a chance, we'll talk about that. But in my modified one, you actually can't represent 0, which is a little shortcoming of my modification. Go read the standards document, or at least the Wikipedia article on IEEE-754, and they'll tell you how 0 is represented. Okay, so these are my mantissa bits, 1, 0, 1. And I'm going to take those and put them up right here. And the last step is, let's do the exponent. So we got 4 bits we can use for the exponent. Here our exponent is 3, but we're not just going to put the number 3 up in the exponent. We're not just going to put, 0011. Because the exponent needs to be able to represent both positive and negative values. The exponent could be negative to represent really small values. And so the exponent happens to be stored not in 2's complement, like you'd think. It's stored in excess n. There's also a very good reason for that. It was not arbitrarily chosen. But excess n is the representation used for the exponent. So we've got 4 bits to use for the exponent, which means there's a total of 16 values we could store there. You following along? So 4 bits means there's a total of 16 values we could store there. And we want about half of them to be positive, half to be negative. So that means we're either going to use excess 7 or excess 8. Remember, the excess n allows us to slide the number line over by that constant amount, either 7 or 8 in this case. And so excess 7 will give us 8 positive values and 7 negative values with 0 in the middle. Excess 8 will give us 7 positive values and 8 negative values with 0 in the middle. So the IEEE folks have decided that if you're doing excess, or if you have 4 bits, you're going to use excess 7. You're going to get 8 positives, 7 negatives. So for 4 bits, use excess 7. Okay, it's basically, you just the way you figure out that number is you take the number of bits you have, you do 2 to that number of bits to find out the total number of values. So 2 to the 4th becomes 16, and you just cut that in half and subtract 1. So 2 to the 4th becomes 16. You divide that by 2 and you get 8, and you just subtract 1 and you get 7. So that's the excess amount. Okay, so we have an exponent of 3. And we want to represent that in excess 7 notation. From last time, we learned that all we have to do is just simply offset that number by 7. So it's really easy. Just take the 3 and add 7. That's all we have to do. And we get 10. 3 plus 7 is 10. That's in base 10. So now we just have to convert that into base 2. That's 1010 in base 2. And that's the number that we put up there in the exponent. And that's it. That is our floating point binary representation of 13.75. It's got a positive number. The exponent is 3. And the mantissa is 1.101. Okay, I know that seemed like a lot, but luckily this is all being recorded, so you can go back and look at it again. But let's try to decode this bit sequence. So somebody has just sent this to you. 1010101, and you need to decode that and figure out what the value of that is. And we've agreed this is going to be an IEEE-754 number using the same representation, the same modification that I just showed you. That means the first bit is going to be the sign. The middle 4 bits are the exponent, and the last 3 bits from the mantissa. And so let's try to decode this and figure out what value this is. Let's take care of the sign first. Now Andrew says, no wonder floating point operations are so expensive on the processor. Yeah, it's going through a lot of work to do that conversion. And also just things like the arithmetic operations are complicated because I just want to add 2 numbers together. You know, if you're doing it with scientific notation, the first thing you have to do is get those exponents to be the same. So you have to change the exponent and then slide that radix point around. Then you can do your addition. Then you got to work with the exponents, and then you got to renormalize it back. So that's why there's in modern processors almost in some cases almost half of the physical silicon space on the processor is taken up just for the floating point operations. So not only the representation is huge, right? 64 bits or so. There's just a lot of steps. Anyway, so we're decoding this. So the first thing is to handle the sign. And that's easy. This is a 0, so 0 means this is positive. And we'll take care of the exponent. So the exponent is 1010. That's in base 2. Let's convert that into base 10. Let's just do a straight 8421 into base 10. We get the value of 10. But we know this is an excess 7 representation of it. So the number is not actually 10. It's 10 that's been offset by 7. So we have 4 bits, which means we're using excess 7. We're going to take the 10, we're going to subtract 7, and we get 3. And that's the real answer. That's the real exponent. Now let's work on the mantissa. The mantissa is 101. But we can put back the 1 dot that we got rid of. So the real mantissa is 1.001. 0.101. Okay, now we have all the pieces, so let's just assemble everything. We have positive from our sine. We have 1.101 from our mantissa. And then we have times 2 to the third power from our exponent. And the last step, just to see what this value is to go ahead and denormalize it and then convert it back into base 10. So we have, let's see, 1101, right? I took this exponent and I slid the radix point over by 3. So I get 1101, and then just for completeness, 0.0. And then we have 8421.1 half. And then we add those up and we get 13.0. So this number here, this 8-bit number, which was represented using our modified IEEE-754, is decoded into the number 13. Now, sharp observers might recognize that this was the same bit sequence that we came up with here when we took 13.25 and converted it into this representation. So when we decode the number, we don't end up with the original number. We end up with 13, not 13.25. So there's been some loss of precision. The number got rounded. Anyway, let's do that again. We'll get to the whole rounding thing here in just a couple of minutes. So let's try to decode this one. We have 100111010. So we'll follow the same steps where the first bit is the sine, the middle 4 are the exponent, and the last 3 are the mantissa. Okay, step number 1, let's handle the sine. We've got a 1 there, which means this is a negative number. Then we'll do the exponent. The exponent is 0011 in base 2, which is 3 in base 10. But since we're using XS7, this number 3 has been offset by 7. So the real answer is 3 minus 7, which is negative 4. Okay, so 3 is not the exponent. 3 has been offset by 7, so the real exponent is negative 4. The mantissa is 010, and we can put back the 1 dot that we got rid of when we converted it into this representation. Next, we'll assemble all the pieces. It's a negative number. We have 1.010 times 2 to the negative 4th. Okay, the negative came from here. The mantissa went here, and the exponent went there. And then the last step is to denormalize. And then convert into base 10 so we can see what the value is. Okay, so negative 4 means we're sliding the radix point over by 4. And we have negative 0.000110. Sorry, just for consistency, I'm going to do that in green. And then if we convert that into base 10, we've got, if I write my powers of 2 here, we've got half, quarter, eighth. So that's a 16th, and this is a 64th. So a 16th plus a 64th. Negative. Let me see, what does that come out to be? Let me use my calculator. This is 0.078125, and the number is negative. So even with this 8-bit representation, with 4 digits for the exponent and 3 digits from the mantissa, we can represent some numbers that are really small, like this one here, 0.078125, and we can represent some numbers that are larger, like 13.25, although it gets rounded to just 13. So we don't have a huge range because we're dealing with a fairly small number of bits, but we do get the ability to represent small numbers and bigger numbers because we're moving that decimal point around. I was wondering if you wanted to do one more decode or if we should just move on. Let's just move on. I had one more decode for you. That was this one here. You could work that out on your own. But same idea. Got your sign. Oh, for this one here. Oh, yeah, maybe we should work this one out. How about this? You figure this one out on your own. What I'm doing here is I'm showing you a representation that uses more than 8 bits. So maybe for this one, I will say that the next 5 bits are the exponent, and the remaining 4 bits are the mantissa. So you'll go through the same steps. I'll just kind of like give you some hints on here, and then you can figure it out, like I said, on your own. First, you'll do the sign, and same thing there as before. 0 equals positive. Then we'll work on the exponent. So we have 10111 in base 2. That is equal to 23 in base 10. Okay, but this is not excess 7. This is going to be excess something else. Because we have 5 bits for the exponent, that means there are 32 combinations. So there's a formula you can use for figuring out what is the excess amount. So for n bits, you're going to use 2 to the n divided by 2 minus 1, and that is your excess amount. Okay, so step 3, mantissa. You've got 0, 1, 1, 0, and then put back the 1 dot. And then 4, assemble. And then 5, denormalize. And then figure out what the original number was. Actually, what I should do here is, just so there isn't any confusion, I'm going to use here for b bits, it's 2 to the b divided by 2 minus 1. Just so you don't confuse the n that I had here with this n over here. It's not the same n. Okay, so this is what I'll leave you with here. So using this representation of 8 bits, where we have a sign, an exponent that uses up 4 bits, and a mantissa that uses 3, what is the smallest positive value that this can represent? Now we know this can do both positive and negative values because of that sign bit out in front. What's the smallest positive value that this notation can represent? And I'll give you a hint. The smallest value has a 0 for the sign. It's got the smallest exponent we can do, which is all zeros. And then it has the smallest mantissa that we can do, which is also all zeros. Now, in the real IEEE 754, this number here is actually 0, but in our representation, it's a little bit more than 0 because of that 1 dot that we end up putting back. So there's always going to be at least a 1 somewhere in the number, which means you're never going to be able to get 0. But what is this number? If we were to unpack this and decode this, what number would we get? I know some of you are probably working it out, but basically we would get positive 1.000, so that's our mantissa, times 2, and remember this exponent here, which looks like 0, has actually been offset by 7. So we're going to subtract 7 from it to get the real exponent, and that is negative 7. So we got 1 times 2 to the negative 7, and Andrew's got the answer there. It is 1/128th. That is the smallest positive number that this can represent. What is the largest number? Largest positive value? So we're going to have 0 for the sign. We're going to have the biggest exponent we can do, which is all 1s. And we're also going to have the biggest mantissa that we can do, which is also going to be all 1s. So what is this value? Positive 1.111 times 2 to the, now again, this looks like 15, but it's been offset by 7. Subtract 7 from 15, and you get 8. So 1.111 in base 2 times 2 to the 8th, which is 256. So if you work that out, you get 1 plus a half plus a quarter plus an eighth. That's the mantissa portion, all times 256. You can just work that on a calculator. Typing it into my computer's calculator. And we get 480. So that is the largest number this can represent. So again, we can put this on a number line. We've got 480 out here all the way on the right. In here in the middle, we've got 1/128th. And then because this is a sign magnitude number, we can just flip the sign and get a mirror image of all the numbers on the left-hand side. So over here is -1/128, and way over here on the left-hand side is -480. So -480 is the largest negative number we can do, and the smallest negative number we can do is 1/128. There's no 0 anywhere in here. So what is the second largest value? What number is just sitting right next to 480? And it's not 479. What number is sitting right next to 480? Well, we can figure that out. It's going to be positive. Still going to be a large exponent. It's just going to be a slightly smaller mantissa. So we get positive 1.110 times 2 to the 8th, which is, as Andrew figured out, 448. So where on this number line is 460? Well, 460 appears to be right there, in the middle, between 448 and 480. But it's not one of the numbers that this representation can actually represent. We've got 480 all the way on the right, and the next number is 448. There is no 460. 460 does not exist in this representation. Neither does 0. 0 does not exist because we just can't represent it using this particular format. So how many total values are there between -480 and +480? What's the total number of values we got there? Now, if this was a real number line, using the real numbers, there'd be an infinite number of values. There'd also be an infinite number of values in between 448 and 480. There'll also be an infinite number of values between 0 and 1. But this is a notation that's using just 8 bits for the representation. So how many total numbers can we represent? Well, it's 256. We've got 8 bits that we can use, and each of those 8 bits can either be a 1 or a 0. So there's only 256 possible values. If we were to write them all out, which we could do, on this number line, we would get 256 little tick marks. Some of them would be closer together as we had smaller exponents and more numbers for the mantissa, and some of them would be further apart as we get smaller values for the mantissa and larger values for the exponent. So that's what's happening like here. These numbers here that are close to 0, the tick marks are really close together. And as we get further out towards the end of the number line, the tick marks get further apart. So this number line is not shown to scale, obviously. So there's only 256 possible values we can do. And you might say, well, that's not good enough. I actually want to represent the number 460. That's important to me. So you could just use more bits, right? You could go up to 16 bits or 32 bits or 64 bits. So we have an infinite number of values on the real number line between the positive and the maximum and the minimum. But we have a fixed number of actual values we can represent. So in between -480 and +480, There's an infinite number of values that are actually there, but we can only represent 256 of them. And here's kind of like the eye-opening thing. What percentage of the total number of values, the infinite number of values, can we actually represent? It's 0. Well, or close to 0. Asymptotically close to 0. Right? We can only represent 256 out of the infinite number of values that are there. So 0% of them. And if we throw more bits at it, if we say, let's use 32 bits for our representation. So now we've got this huge range of numbers we can do, but we can only represent about 4 billion of them, which still seems like a big number. But out of the infinite number of values that we need to represent, we can only represent actually 4 billion of them, which is still 0%. And even if we threw 256 bits at this problem, now we've got this enormous range of numbers. An enormous number of values is huge, but we can still only represent 0% of the actual numbers. And this is kind of a fundamental problem for engineers and financial people, is that whenever you try to represent fractional numbers, unless it happens to be a nice round power of 2, there's always going to be some rounding involved. It's always going to be like a little bit more or a little bit less than the actual value it needs to be. And so I just want you to be aware that whenever you store floating point or double numbers, there's often a little bit of error that creeps into your calculations that tends to magnify itself as you do more and more calculations. Now, the IEEE folks have also in their documentation listed out some ways to mitigate those problems. When it rounds, it uses a slightly different technique than we were taught, like in grade school. In grade school, we were taught like, if it's 0.5 or more, or 50 or more, or 5 or more, then you round up. Otherwise, you round down. But there's actually an asymmetry involved with that, right? If you round up, you're going to round up the 5, 6, 7s, 8s, and 9s. So there's 5 digits to get rounded up. But if you round down, you're only going to round down the 1, 2, 3s, and 4s, right? So there's 4 digits that get rounded down, and there's 5 digits that get rounded up. So there's a little asymmetry there. And so I think one of the things that IEEE-754 says, that if the number is 5, then you look at the next digit. And if the next digit is even, then you round up. And if it's odd, you round down. Right? And what that does is it splits that asymmetry in half, so that half the time you'll round up and half the time you'll round down. And that makes the error kind of cancel out as you do more and more calculations. So that's one thing that they use to kind of mitigate these problems. Another technique they use is there are representations for special numbers. And by special, I mean there's a representation for infinity. There's a special bit sequence they use to represent infinity. There's also a special bit sequence that's used for not a number. If I was to take a number like 5 and divide it by 0, if I do that in integer arithmetic, my program is just going to crash. Division by 0 error. But if you do it with floating point numbers, you get not a number. And what that means for your program is that when you do a division by 0, it's not going to crash. It's going to display NaN, not a number, but it's not going to crash. And then once you get to NaN, you can never get out of it, right? You can never like take 2 and divide it by 0 and then multiply by 0 and get the 2 back, right? That's not going to happen. But at least your program won't crash. And the same thing goes for infinity. If you do a calculation that results in the answer being too big for it to represent, then it just represents the number as infinity, and then you can never get out of that. At least your program won't crash, and it won't do this mysterious thing like it does for integers where it rolls over to the negative numbers. It'll just pin itself as infinity, and then that number propagates through the rest of your calculations. Okay. So now you've got an idea about how floating point numbers are represented in the computer. We did it with 8 bits. The real ones use more bits, but the idea is the same. A single bit for the sign, a certain number of bits for the exponent, and a certain number of bits for the mantissa. I know that was a lot to throw at you. We covered like all of that stuff in one 90-minute session. And this stuff is also not in the book that we're using. And you also really kind of can't, I mean, I think if you look hard enough, you can find the material that I got this from, where the person who wrote this was using 8 bits and split it up the same way that I did. But for the most part, if you go and find an IEEE-754 converter for you, it's going to use the real one that uses 32 bits or 64 bits or 128 bits. And it's not going to be useful for doing the 8-bit one that we're doing here. But it will be useful to study, to see how the exponent and mantissa are broken up. And you'll see that they use the same technique that we did. They drop off the one dot, just like we did. They use excess n for the exponent. They're just using bigger numbers. So that's what I have for you right now. We're now going to take a break for about 10 minutes or so. And then we're going to come back and we're going to go over lab number 1, your first Python programs for this semester. Okay? So, Zoom people, I'm going to pause the recording so you don't see the break. And then YouTube folks, we're going to have a 10-minute break or so. All right, so I'll see you in about 10 minutes.
Recording stopped.
Now some more intermission music. Seems like I lost most of the YouTube folks. I'm down to 0 viewers right now. That's all right. Actually, YouTube folks, I think, unfortunately, probably going to say goodbye to you at this point. In part because the lab assignment that the students are going to be working on is not something you can get access to. You don't have the files, you don't have the website. I don't know. I mean, should I or should I not? You know what I could do is I could just continue with the live stream, and if I decide it's a problem later on, I can edit it out. So maybe I'll keep you on for a moment, a little while, and then see how that goes. So what we're going to be doing is starting with some Python programming. We're just going to be going over the basics of it, but this is not like a full-blown Python programming course. It's enough to illustrate the concepts that we're trying to get across. Basically using Python as a big calculator. So it might be interesting to learn about some of the things Python can do, but like I said, you're not going to have access to the files we're using. How are the rest of you doing? People who are actually on Zoom listening in. Not too bad?
I'm great.
Good? I know it was a lot of stuff to throw at you, but...
I've been on Zoom since 7:30. I just made breakfast while watching the call.
Wow. What else were you doing? Were you watching other classes?
I first had chemistry from 7:30 to 8:30, and then right at 8:30, I had a data structures meeting from pretty much 8:30 to 9:15, and then I joined the lecture for this class right after.
Whoa. How's that data structure course going? Is that the one at Sierra?
Yeah, it's taught by Araj.
Uh-huh.
I forget his last name.
Yeah, I know who you're talking about.
It's pretty good. I definitely prefer the structure of this class, just because you post more like concise, organized videos, and his are more just like lecture videos where you kind of have to watch him teaching one of his older classes. So it's just like an old recording from one of his lectures.
Yeah, I like doing the live stream stuff. And I really appreciate that you all are taking the time out of your day to come and watch this. It's only, 8 of you? But I get the feeling it's going to be the same 8 for the rest of the semester. So that's going to be good to kind of get a consistency and some regularity to it.
I enjoy it because we can ask questions.
Yeah. Well, somebody else was going to say something?
Yeah, I tried to set up my schedule this semester so that I would start at 11 and go until later in the day. This class didn't have a time period, so the fact that it starts at 9:30, it happens to slot in right before that, but I'm not always awake then.
Oh.
So I'll make it when I can.
Good.
Which is why I wasn't here on Monday. What was her name? Last semester I had data structures with it was Gita.
Oh yeah?
Yeah.
I didn't know she was teaching that class.
She's a great teacher.
I did notice a couple of interesting things in that class. All of the tests, the multiple choice tests, the answer was always the first one.
Oh my goodness. I think I know why that happened.
Yeah. Well, it's interesting because the questions were laid out as A, B, C, and D, and then when you can select them, it would be like C, A, B, D. If C was the correct answer.
Huh.
Yeah, it seemed like there was a something going on that was very distinct.
Well, either she was psyching you out, right?
Yeah.
or she forgot to check the box that says shuffle the answers, shuffle the choices on the quiz.
Well, even then, it was shuffled in such a way that the correct answer was always shuffled to the top.
Huh. And then someone else in the chat said the same thing happened to them. And same thing happening in the 13th class.
It was teaches CS13 too, and she did this.
Same things happening?
Yeah, it was the CS13. I guess that's not data structures, is it? It should be. I thought that's what that was.
Programming concepts and methodology too. I think that's the title of the class.
Okay.
It's like more object-oriented programming with Java.
Yeah.
With a little touch of data structures like hash maps and lists and arrays.
It's all stuff that I'd done before in when I was at Chabot College. It's just we had a different class for it.
Yeah, it's the same, almost the same thing as pretty much the same thing except for one topic as the high school like AP Computer Science A class.
When I was at Chabot, we had we did the same thing in C++ instead of in Java, and it was I actually took 3 classes in C++. There was CS1, CS2, or I guess CS. I don't remember what the numbers were, but it was the intro to C++ and then advanced C++, and then we had data structures. I passed the first 2. I could not pass data structures. Of course, that was 10 years ago. So.
Well, I'll have to drop her a note about the choices always being the first one.
I tried to mention it, but I don't think I did it very well.
Oh, let me stop the music. It's about time to get going again. Okay.
Recording in progress.
So we're now in what would be the lab portion of the course. If we were actually in a classroom, we would have spent 9:30 to 11 o'clock in the classroom. Then we would have gone next door to our computer lab, and I would be talking to you about the assignment that you were doing for the week. So we're kind of doing the same thing here. On Wednesdays, that's what we do from 11 to 12 o'clock, as we go over the assignment for the week. The first half of the semester is pretty heavy on the assignments, so we've got 1 per week. And then when we get into the second half of the semester, it lightens up a little bit. So we're kind of like on this roller coaster, right? We're going up, 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 up. And then halfway through the semester, we'll crest that, and then we'll come down the other side, and it'll be more smooth sailing on the other side. Or it'll be like like a roller coaster. It'll be terror, but no, it won't. So looking through our Canvas course, where we've now done all the stuff at the top. We've done sign integers, which is down here. And then we've done this floating point representation, which is here. And we're down into lab number 1. And I've got these other sections here called Dive Deeper. And these are some assignments you can do. I believe they're multiple choice assignments where you can dig a little bit deeper into things like binary representation and base 16, base 32, base 64, and just have fun decoding some of these representations into plain text. In fact, a couple of weeks ago, I did an escape room with my wife and some family friends. That was a whole lot of fun. It was like your standard escape room where you've got some puzzles to solve. And if you solve the puzzle, you get the combination to a lock. And then you unlock that lock, and that unlocks some other puzzles that you can solve. And so I kind of like thinking of these particular deep dives as being kind of like an escape room where you've got like these puzzles to solve. And if you do solve them, it's obvious you've solved them because you get some text that you can read. But if you aren't able to solve it, you still just get gibberish. Right? So try your best to solve them. You can just paste your answers into Canvas, and it will check to see if you've got the correct answer. Try to paste them as best you can. If you've got extra spaces on the front or the back, then it'll mark them wrong because that's not exactly what it's supposed to be. So just make sure there's no extra spaces when you decode things and encode them. Okay, so we're on to lab number 1. Let me click through to that. And because we are trying to learn Python, this one. Because we're trying to learn Python, I have, in many cases, broken up the assignment into 2 parts. There's lessons to just walk through, and then there's the actual assignment that you turn in. I think for getting started with her, there's only one thing to do, so just be aware that in future weeks there might be 3 or 4 things to do. Of those, only one of them you'll actually turn in. So we're going to be using a programming language called Python. And one of the reasons why we're not using Java or C or C++ is because Python happens to handle the kinds of data natively that we want to work with. We want to work with, in some cases, really big numbers. Python handles those without breaking a sweat. Java and C kind of max out at 32 bits for their integers, and then you can't represent any numbers that are bigger than that without diving into some of the classes and libraries they provide for you. And using the big integer libraries with Java and C++ is just a real pain, because you got to create objects and call methods, and you can't just write out arithmetic expressions and have it do the calculations for you. So that's one reason for using Python. Another reason for using Python is it's actually really popular among people like data scientists and bioinformatics people and increasingly computer scientists. Python is becoming more and more popular, in part because it's just so easy to get started doing Python programming. There's not a whole lot of like excess syntax you have to learn. You don't have to get braces in the right spots and semicolons. It's pretty, well, it has its own syntax. It's going to be familiar. It's just not as like rigid and structured as it is in C or Java. You still have to do things like structure your code, you know, for ifs and else and loops and things like that. There's a different way to structure them. But I think it's not as kind of like scary to beginners of seeing all these weird symbols all over the place that you have to get in exactly the right spots or it just won't work. And then the third reason to use Python is not all of you know it. It's brand new to a lot of you. So it's something new to learn, but also for me as an educator, it helps to kind of level the playing field. You got some people coming in who are pretty good at Java and some that are not so good. You got some people that are good at C and C++ and some people that are not so good. And so by teaching you a language that not everyone knows, in fact, most of you probably don't know, everyone kind of starts out equally confused, and you grow from there. So Java is a good language to learn. It's used by increasingly a larger number of people in the real world. It's something that not all of you know, so it'll be a new thing to learn, and it does actually happen to handle the kinds of data that we want to handle in this particular course. I like to provide development environments for my students that are just web-based. Increasingly, I think we're headed in that direction as an industry towards doing more stuff on the web rather than doing it on our computers. And so I'm providing a web-based development environment for you, which is great because it means there's no software for you to install and maintain. All you need is a web browser, and you can get access to all the files that you need to do these assignments. There is a way to install this environment on your computer. I'll leave that up to you, but you could do it in Visual Studio Code and install the Python extension. The problem with that would be primarily you don't have access to the same files that I've pre-installed for you. So that would be entirely up to you. If you absolutely have to do it on your computer, I can contact me and I can kind of point you in the right direction to get things working. But I'm providing this environment for you. I know it works, it's available, and so I would encourage you just to use that. So Python, being a traditional programming language, you can develop your programs in a more kind of traditional way. You could bring up a development environment that has an editor for you to type your program in. It's got some way for you to run the program and see the results. And it's got maybe some kind of like project or file browser where you can see your files. Right? That's kind of a traditional IDE setup. But there is an alternative. Python happens to be good at this. And there's an IDE called Jupyter, spelled with a Y instead of an I. And a Jupyter uses a setup called a notebook, where you can intersperse text and code. And then when you run your program, behind the scenes, it takes all the code out of your notebook and packs it all together and then runs it. So rather than your code being all in one place, I'll show you in a moment here, you can have some text where I can explain what to do, and then a box for you to type in some Python code and try it out, and then some more text where you can have some explanation, and then a box for you to type in some Python code and try it out. Also with Python, there's no explicit compile step. You just simply type in your Python code and click run, and it runs it right there on the spot, and you can see the answer right on the screen. So I think it's a great environment. I just want you to be aware that what you're seeing is just a user interface to the Python programming language. That is not the Python programming language. The Python programming language is not the notebook format. The Python is the stuff in the boxes. Okay, so you can do Python programming in a traditional way, or you can do it in this notebook way, which is great for kind of an educational setting. Okay, so let's take a look at it. So the first thing you need to do is log into Jupyter. So when you bring up the Jupyter website, and there's a link provided on our assignment page here, you'll be, let me go ahead and log out and show you what it looks like. You will, oops, this is what you need to look at over here. So when you log into Jupyter, which is, again, a link is provided on our website, you'll be presented with a sign-in page. So you are going to type in your campus or My Sierra username, and then for the password there, you're actually going to be setting up an account here. This looks like a login page, but it's actually an account creation page. So type in your My Sierra username, and then just pick a password here. It doesn't actually have to be the same as your My Sierra password. Whatever password you type in here, and it's not going to show it to you, whatever your password you type in here will be your chosen password for our website. So it won't show it to you. So what I might suggest you do is type it in something where you can see it, like in Notepad or TextEdit, and then paste your password into the password field. It'll just show you a bunch of dots. And then when you click on sign in, it'll set up an account on Jupyter, and it will use that password you picked as your password from that point forward. Someday, I'll get around to tying this in with the campus authentication server so that you can just type in your My Sierra username and password and it'll work. But for now, this is the way it's going to go. Not anyone can create a password and username on here. It's only a designated set of users that are actually enrolled in the course. So I have preloaded the usernames into the system, and you're just picking a password. Okay? So go ahead and type in your My Sierra username and pick a password, and then click on sign in. Andrew asks, can I overload the operators in C++ to make the data manipulation easier? Yeah, actually I could do that. However, Python's just easier because all that stuff is already built in. And we don't have to learn C++, we're learning Python. Once you get logged in, you're going to see this file browser here. Right now it's empty. We're going to have to upload our assignment documents into Jupyter and then start working on them. So I guess I'll wait for a few moments and let you get caught up so that you are now seeing this screen here. So if you're on Zoom and you're watching this, just let me know with like a raised hand or something that yes, you've got this far. You've got to this screen. I don't know if you've noticed here, but on some versions of Zoom, if you actually have your camera on and you actually raise your hand, it'll like recognize that you're raising your hand and it'll raise a hand on the little thumbnails. Has anyone noticed that? And if it doesn't happen to you, I think it's a setting you can turn on to recognize these gestures. So you can do like a wave, you can do a thumbs up, and it'll actually put the little emoji on your icon. That startled me one time. I was like waving. I think I was waving to someone who was walking past me in my home office here. I just went hi, right, and then boom, the little icon appeared on my the little emoji appeared on my icon. I went, whoa! I didn't know it did that. That's kind of cool. So it looks like the majority of you are at this point. So let's go back to the assignment page. And there is a file for you to upload into Jupyter. So you need to download this file to your computer and then upload it to Jupyter. So I'm going to click on this file, and then it's going to download to my computer here. So here it is right here. And then I'm going to flip back over to Jupyter, click on this upload button, and then go and find that file, which is So I got a lot of stuff in here. I need to clean up my computer. Oh, here it is. lab1.pynb, Python notebook. And then click on upload, and there it is. Okay, so download this file to your computer, and then click on upload back on Jupyter. Go find that file, it'll probably be in your downloads folder, and then upload it to Jupyter. And then click on it. And it'll open up a new tab, and then this is the Python notebook. You can see there's some text, and then if you scroll down, there's some boxes where you can try out or type in some Python code. So let's walk through this from top to bottom. You can follow along, and then when we're all done with this, you can turn in this file as your submission, and then I will mark it as complete or incomplete. Okay, so let's start at the top. So Python is a full-featured programming language. It's often billed as being somewhat easier to learn than things like Java or C or C++. You can use a traditional IDE with an editor and a compiler and a place to run your programs, but this notebook format is great because I can intersperse some instructional text along with boxes where you can type in your Python code. Each one of those boxes is called a cell. It can contain text, like the one that you're reading right now, or it can contain Python code. So let's get started with some simple Python arithmetic. So the first thing to know here is that Python supports all the usual operators like plus, minus, times, divide. It also supports modulo or remainder with the percent sign. So does C and Java. But it's got a couple of new ones. It's got 2 slashes, which is used for integer division. So 1 slash is used for floating point or decimal division, and 2 slashes is used for integer division. It'll give you just the quotient of the division. And the other operator you should know about is the double star, which is used for exponent. You don't use the caret like you'd think you'd use. You use 2 stars to do exponent. Okay, so let's try it out. So I've already typed in some Python code for you. All you have to do is execute each one of these cells. There's a couple ways you can do it. One is you can click in the cell and then click on the run button up here at the top. Depending upon what browser you're using or what size screen you're using, there may also be a run button off to the left-hand side. My screen is big enough that I don't have that. I think if you do this on like tablet screens or smaller screens, you do have that run button over there. So that can be kind of convenient. So you can click on the run button. You can click on the run button over here on the left-hand side, or you can just press Shift-Enter or Shift-Return, and that'll also execute the cell. That's the way I prefer to do it because my hands are already on the keyboard. So I'll do the first one by clicking on Run, and you'll see that it opens up a little space below the cell and it shows you the answer. And then for the next one, which is 123 raised to the 456 power, I'm just going to press Shift-Enter, and it will execute that cell. And you can see that's a pretty big number. That's way bigger than 4 billion, which is the largest integer that Java could do. It's way bigger than the long integers, but Python, you see, had no problem handling this. And then finally, we can do 92 raised to the 5th power modulo 19. Shift-Enter, and you can see the answer is 4. So let's just try out some stuff. Now, we are running on a shared server, so anyone who is watching right now, which is all 7 of you, are probably logged in right now and following along. You can actually type in a calculation that will make the program have to do some work. So if you type in like a really big base and a really big exponent, you'll be sitting here a while. So try to keep the numbers, smallish and not too excessive. But if your program takes up more than half a gigabyte of memory, it'll just be shut down and the calculation will be aborted. So let's just type in something like, this. Let's raise to maybe this power. Go ahead and Shift-Enter. I always like entering big numbers and see what happens. So, wow, that is a huge number. But you can see Python just went ahead and calculated that. If you want to insert a new cell, just click on the cell that you want to insert below and then click on this plus button right here. And it'll open up a new cell. You can put in some more Python code. Let's see. Oh, so that one it's working on. Look here. I don't know if you noticed that, but inside of those brackets there was a star for a while. That star means the processor is working on your calculation, and it'll get back to you in a few moments. And then as soon as a number appears there, then the calculation is done. So this number basically is incrementing. It started out at 1, and it's gone 2, 3, 4. So this is basically, calculation number 5 that it has done. All right, now that's a huge, even bigger number. Yeah, I'm not going to scroll all the way through that. Okay, next thing to do is Python understands numbers in other bases. Normally when you type in a number, it assumes it's a base 10 number. But if you put the prefix 0b in front of the number, it will then interpret the number as a binary number. If you put 0o, it'll interpret it as an octal number, and 0x means it interprets it as a hexadecimal or base 16 number. So we can go ahead and try this out. Here's 0b 1100110. If I press Shift Enter or Run, it will convert that into base 10. Or it'll just tell me. It won't actually convert it. It's already in binary inside the computer. It'll just show it to me in base 10. Here's hexadecimal number, and then here's another binary number. And you can also do arithmetic in these bases. And you can mix the bases up. You could do a number in hexadecimal added to a number in binary. Or you can do a number in decimal added to a number in octal. Right? It'll just go ahead and do the calculation for you and give you the answer. And then finally I wanted to show you that you can convert between bases. So I can take a number like 1, 2, 3, 4, 5 and convert it into hex, binary. I can convert hexadecimal to binary, and I can convert binary to hexadecimal. Now the answers it gives to you are enclosed in quotation marks. That means it's a string. And the reason why it has to give you the answer in a string is because it contains that prefix on there, like that 0x or the 0b. Anything that's not enclosed in quotation marks is assumed to be a number. And with those prefixes on there, it's not a number anymore. So in order to keep it as a string, it has to put inside quotation marks. And then finally, you can do calculations in any arbitrary base. You can do base 3, you can do base 26, you can do base 32. All you have to do is call the int function, pass in the number you want to convert, put it in quotes because it's probably not going to be just a base 10 number, and then put in the base that number is represented as, and it will convert it to you to base 10. Okay, we're good so far? So I'm just doing a walkthrough real quick. You take your time to do this. You can, if you're watching this afterwards, pause the video, try it out, unpause the video, try it out, pause the video. So next, strings. Strings in Python are a lot like strings in C or Java, with a couple of differences. First difference is, it doesn't matter whether you use single quotes or double quotes. In Python, they're pretty much the same. In C or Java, single quotes means it's a character, and double quotes means it's a string. In Python, it's the same thing. So a character is really just a string that only has one thing in it. So it doesn't matter whether you use double quotes or single quotes, use whatever is most convenient for you. And you can also concatenate strings just like you do in Java with the plus operator. So far, everything has been pretty much kind of review from Java or C. The primary differences have been Python handles big numbers very easily, and it has a couple of extra operators that are going to be useful for us. Integer division and exponent are going to be useful for us. And also, strings are represented either with single quotes or double quotes. Doesn't matter which one you pick, just pick whichever one is easiest. Whichever one you start with has to be the one you end with, so you can't start with double quotes and end with a single quote. But otherwise, pick whichever one you think is most convenient. And then finally, Python understands ASCII and Unicode values. Actually, everything is Unicode. It's no longer just ASCII, so we can do things like represent emojis with it. The ORD function can be used to find out what is the Unicode value of a particular character. So the Unicode value of the capital A is 65, of the percent sign it's 37, and of the smiley emoji it's 128,758. So here's a question for you. What's the Unicode value of the snake character, which looks kind of like a Python? So what could you type into this box here to find out the Unicode value of the snake? Now, if you don't know how to type the snake, then just go ahead and copy the snake and you can paste it in here and then use the ORD function to find out the Unicode value of that snake. Don't forget to put it in quotes, just like it is in the previous examples. Did that help? Did that solve the problem for you? Okay, good. Got through that. All right, now here's something new that Python has. Internally, strings are just arrays of characters, sequences of characters. And that's the same also in Java and in C. They're just an array of characters. But we've also learned that characters have a huge range of values, anywhere from 0 up into the hundreds of thousands. So therefore, strings, being arrays of characters, can have lengths that vary. So even though they might appear to have only 5 characters in it, the number of bytes that the array actually holds may be anywhere from like 5 to 30. And that's not always most convenient for us in the kind of things that we're going to be doing over the course of this semester. So Python has another kind of string, if you will, in which each one of the characters is exactly 1 byte. Not a variable number of bytes like it is for normal strings. These are called byte strings because every character is exactly 1 byte. It's an array of bytes rather than an array of characters. Okay, so this is called a byte string. They are represented just like regular strings, except there's a B in front. So here's a string, which is a sequence of Unicode characters, and it's enclosed in double quotes or single quotes. Here's a byte string, which is a sequence of bytes rather than characters, and it's also enclosed in double quotes or single quotes, but there's a B sitting in front to say that this is a byte string, not a regular character string. Byte strings are useful for us as programmers in this particular course because there are going to be times when we need arrays of bytes. We want to know how big that array is exactly, and we want to deal with each character in the string on a byte by byte basis. Okay, so that's coming up later. And then we're going to finally end with base 32 and base 64 encoding, which I showed you last week. And if you do the deeper dives, you're going to be playing around with base 32 and base 64. In fact, you may want to use this Python notebook to help you out with some of those deeper dives. So these are the last 5 or 6 things in the assignment. To do base 64 or base 32 encoding or decoding, you need to import the base 64 library. So this is a set of Python code that someone else wrote that will convert strings into their base 64 representations, and it will also convert the other direction. So if you execute this cell, press Shift Enter, and you'll know it's been executed because there's a number sitting here. And then you execute the next cell, it'll take that byte string hello and convert it into its base 64 equivalent also as a byte string. So base 64 cannot convert a Unicode string. It has to convert a byte string because it works on a byte by byte, 8 bits at a time basis. Remember, we saw how it takes your string, it packs all the bits together, and then breaks it up into sequences of 6 bits and then does the conversion from there. So it needs to work on byte strings in order to do that. So we can encode the river runs through it. We can also decode a base 64 string back into its original string. We can encode into base 32, and we can decode from base 32. So how do you tell the difference between a base 64 and a base 32 encoding? Well, you kind of look for some clues. A base 64 encoding, 2/3 of the time, is going to have some equal signs on the end. So if you see some equal signs on the end, you can be pretty confident that's a base 64 encoding. Also, base 64 encodings use uppercase and lowercase and numbers and a couple of symbols in their encoding. Base 32 only uses uppercase and digits, and not even all the uppercases. It ends at V. So that's another thing to look for. Oh, this particular base 32 also puts equal signs on the end for the same reason the base 64 does. Not all of the base 32 encodings out there do that. But these are just like clues to look for to figure out which one is which. So if you're looking at a particular sequence of bytes and you want to know is that a base 64 or a base 32, you can look for the presence of the equal signs. That'll help distinguish it. Or you can look at the uppercase and lowercase, and that'll help distinguish it. So the last things to do is to decode these 3 encoded strings. So you need to use this technique that I showed you up here to decode them. You need to figure out, are these base 64 or base 32, and then plug them into the appropriate decoding function. And it'll be obvious if you got it right because you'll get some plain English text out of it. If you get more gibberish, it means you didn't do it correctly. If you get something that you can read, you did it correctly. So there's one cell here where you can type in your statement to do the decoding. You'll probably have to open up 2 more cells so that you can get all 3 of them fit in there. Also, these strings go off to the side, so be sure you scroll them to get the whole thing. Okay, so that's the assignment for this week. Pretty easy. Just getting started with Python. Please, you work through the program, and you may want to keep like a little notebook off to the side. Write down things like the Python operators. Write down some of the functions like ORD to figure out the Unicode values of things, and encode and decode, because we're going to need those again. I'm giving this introduction, but I'm setting you up for being able to do the assignments that are coming up. So this is not just like a one-off, I'm going to do this assignment and then I'm going to throw away that information. You're going to need to keep this information and use it later on. That's going to be the case for all the assignments. Everything you learn in a particular assignment is not only going to be applicable to that assignment, but also the future ones. So you have to keep some notes about what you're learning in the lessons so that you can apply them to the future assignments. Okay, last thing is how to turn in this assignment. So in order to turn it in, you need to go back to the Canvas page, and I as a teacher don't see it on here, but you will see a button that says Submit Assignment. You'll click on that button and it will open up a place where you can upload a file. So what you have to do is go back to Jupyter, and you've now got to download the file off of the Jupyter server onto your computer and then upload that file that you just downloaded. To do that, you go File, Download As, and then Notebook File. So let me do this again. File, Download As, Notebook. And it'll put it in your Downloads folder. So here it is right here. And then come back over to Canvas and then upload that file to Canvas and then submit your assignment. The instructions for that are right here, how to turn in the assignment. You're going to go File, Download As, Notebook. Check your Downloads folder for your computer, on your computer. What you're probably going to find is that you now have two files called Lab 1. You've got the original file that was blank or didn't have your work filled in, and you've got this new one that has your work filled in. Make sure you upload the new one. It's probably going to be called like Lab 1 copy or Lab 1 and then a 1 in parentheses or something like that. Some way to distinguish it from the original one. Make sure you upload the new one and not the original one. If I discover that you uploaded the original one, I'm just going to mark it incomplete and give you a note that says, hey, it looks like you uploaded the original one, not the new one. Could you please go and upload the real one? So just because you get an incomplete doesn't mean that you failed the assignment. It just means you just got to turn it in again. Same thing's going to happen if you do the assignment and you didn't, like, let's say, decode those strings at the bottom correctly. I'm going to give you some feedback that says, it looks like you didn't do it correctly. Try it again. And then you can just keep turning in the assignment, keep resubmitting the assignment until you get it complete on it. That's all there is. So I'm just going to mark it complete or incomplete. Incomplete doesn't mean that's the end of the line. Incomplete just means you've got some more work to do. I'd like you to do it. And if you turn it in again and get it all correct, then I'll mark it complete. If it's still not done to completion, I'll give you more feedback and you turn it in again. So just keep repeating that cycle. You can turn it in as many times as you need in order to earn a complete on it. Okay, so that's it. I've done my walkthrough of the assignment. There's only one to do this time. If you want to, you could start looking at the next thing for next week, and that one's going to have 3 lessons and then 1 actual lab file. So the lesson ones are just for you to work through, and the lab one's the one you actually turn in. So you might want to start working through those lessons between now and next week. Okay, so that's it. I hope you got something out of that walkthrough and you're able to complete it successfully. I got a question here. Length? Oh, you mean like for doing the decoding here is the length of it? So the length of it really doesn't tell you whether it's base 64 or base 32. If I encode a short string in base 32, it'll come out to be a little bit longer than the base 64, but not tremendously longer. It has to do more with the length of the original string. So if you encode a long string to begin with, you'll get a long string in the encoding. If you encode a short string, you'll get a short string in the encoding. So this does, the length of this doesn't really tell you what the encoding is. You have to look for things like uppercase, lowercase, equal signs, no equal signs.
Is there a limit to how long you can decode something? Like, does the base 32 decoding have a limit on the length of the string that you input?
No, not at all. No. I could take something like the complete works of Shakespeare and encode it, and it'll happily do that.
Gotcha.
And if you remember last time, I showed you that things like images get represented in base 64 when they're sent through email. And images can be huge, right? So there's no limit. At least none that we're going to run into in any practical sense. Any other questions? All right. Well, thanks for hanging in there today. I know we did a lot of stuff, but we are now ready to move on. So next Monday, we are going to move on to Chapter 2. Chapter 2 is Boolean logic and gates and circuits. We're going to start with gates and circuits first. And that's going to be a lot of fun because we're going to start learning how the fundamental building blocks of the computer are constructed. So your computer is made out of nothing more than basic operations like and or, and not, and nor, and exclusive or. The basic operations aren't even things like add or subtract. There's even more fundamental ones. And you know, computers are actually built, they were at one time built out of chips that just did ands and ors and nots and stuff like that. In fact, I'll show it to you next time. I have one in my closet. That's an actual working computer, and all it is mostly just ands and ors and nots and stuff like that. And then we'll go from there. Like from those basic operations, we'll be able to build adders and registers that hold information, and from there you can build things like bus multiplexers and decoders and arithmetic and logic units, or ALUs. And then from all of that you can build a working CPU out of nothing more than ands and ors and nots. It's really kind of a mind-blowing thing that all of this complicated stuff, it doesn't matter how powerful your computer is, whether it's an i7, an i9, it's got a GPU with 5,000 processors in it, all of those things are just built out of the same fundamental building blocks that just do no more than and or and not. And that's it. So it's really cool stuff. So that'll be next week. Okay? So I hope you all have a great rest of the week. I'll see some of you on Thursday in my other class. And if you're not in my other class, just watch on YouTube. And it's a C programming class. All right. So if there's no more questions, then yeah, have a good day. Take care. Bye-bye. And people on YouTube, let me see. There wasn't a whole lot of chat today, mostly chat having to do with the arithmetic problems we were doing earlier. Now somebody said, that's cool, but I don't know what that was in reference to. And then someone else said, hey, you're back. That's great. I'm glad to see you back. I've actually been back since November, when I just decided to start streaming my classes that I'm doing online on YouTube. So but for the previous 2 or 3 years, because of COVID, I've been just doing Zoom with my classes. I'm sitting here at home. I have been here at home for 2 years now. I actually have not gone into my office in over a year. And then when I had to go in a year ago, it was just to grab a few things and then leave. So it's been kind of like a ghost town at my university, at my college. We started offering some on-ground classes, but then because of this Omicron variant, they decided to go online again. So for the first 2 to 4 weeks, some of the classes are back to being all online. I have never left my home office. In fact, I built this whole set just to be able to do online classes. And so now you can just watch my stuff on YouTube and just follow along as best you can. But my primary audience when I'm doing these classes is the students that are on Zoom. So I'm primarily talking to them. If they ask questions, which you can hear sometimes you can hear their voices, I'm talking to them. If I respond to their chat, I'm responding to them. So the YouTube folks, you can follow along, and I do really appreciate you can, and I will get to your chat messages when I can, but I'm primarily talking to my students. So go ahead, post stuff on the chat, and if there's a pause in the discussions that we're having, I'll look at the YouTube chat and I'll try to answer your questions there as well. So you can see all of my recordings that go back to about, like I said, I think it was about October or so when I started doing this. So we're basically doing that was the second half of the course. And so we're doing the first half of the course. So once you put all of that together, once we hit about March or so, then we'll be all caught up. And I'll just keep going, right? So you'll get a complete discrete structures course from beginning to end by the time we get to May. Same with the C programming course. You'll get a complete course as an introduction to C programming from beginning to end. And you can watch that all on YouTube. Okie doke. Well, I'm going to sign off for today. I've got some work to do, and then I will see you on either Monday to watch the Discrete Structure course again on Monday, or I'll see some of you on Thursday for my C programming course, and we're going to start getting more into functions. We're doing function prototypes and start showing you how things like the stack and local variables work underneath the hood. So that'd be really good stuff. So have a good day. Take care. Hope you enjoy the weather wherever you are, and I will see you next time. Bye-bye.